Jupiter is large enough to hold more than 1,000 Earths, and yet, after centuries of observation, scientists still cannot say with certainty what lies at its center. The problem begins with something we take for granted on almost every other world: a surface. Jupiter does not have one, neither does Saturn. There is no solid ground waiting beneath the clouds. Descend into either planet, and the atmosphere simply becomes denser, hotter, and more compressed until the distinction between gas and liquid begins to disappear. And eventually, familiar matter starts behaving in unfamiliar ways. Deep inside Jupiter, hydrogen is squeezed under such extraordinary pressure that it can enter a metallic state, conducting electricity rather than behaving like the hydrogen we encounter on Earth. We have tried to enter this world once. The Galileo atmospheric probe descended into Jupiter in 1995. It survived for less than an hour before communication was lost, as it plunged into conditions no spacecraft had ever experienced. And that descent barely touched the planet's enormous interior. Saturn presents a different mystery. Its familiar golden clouds conceal an interior under pressures capable of transforming ordinary elements in ways that sound almost fictional. Scientists have even investigated whether carbon deep inside the planet could crystallize and fall through its interior as diamonds. But perhaps the strangest discoveries concern the centers of these planets themselves. For decades, scientists pictured gas giants forming around relatively compact cores, buried beneath immense layers of hydrogen and helium. Measurements from spacecraft have made that picture much less certain. Jupiter's deepest interior appears more complicated than the simple core scientists once imagined. Saturn has produced its own surprises, with clues to its hidden structure encoded in something visible from millions of miles away. Its rings, two enormous planets, no surfaces, no direct view of their deepest interiors, and hidden beneath their clouds are forms of matter and planetary structures that we are still trying to understand. Before we go any further, if you enjoy exploring the cosmos with us, a quick like or subscribe goes a long way. It helps us keep making these deep dives for curious minds like yours. Now, let's begin. Long before the planets had names, the young sun was surrounded by a broad, rotating disk of material. Astronomers call it the solar nebula, a mixture of hydrogen, helium, dust, ice, and heavier elements left from the cloud that formed our star. About 4,600,000,000 years ago, that disk became the construction site for everything now orbiting the sun. Timing mattered enormously. Gas does not remain available forever around a newborn star. Radiation and powerful stellar winds gradually clear the surrounding disk, giving giant planets only a few million years to gather their enormous envelopes. Jupiter appears to have formed early, probably within the solar system's first 3 million to 5 million years. Saturn followed while enough material still remained farther from the sun. Out there, temperatures were low enough for water and other volatile substances to freeze. Solid material could accumulate efficiently, allowing planetary embryos to grow faster. In the leading model, called core accretion, Jupiter began with collisions among countless small pieces of rock and ice. These assembled into a massive central seed, perhaps around 10 times Earth's mass. Once that growing body became sufficiently heavy, its gravity began capturing hydrogen and helium from the surrounding nebula at an accelerating rate. The result was runaway growth. Jupiter accumulated roughly 318 times Earth's mass. Saturn eventually reached about 95 Earth masses. Together, the pair now hold roughly 90% of the mass contained in all the solar system's planets, giving them gravitational influence far beyond their visible atmospheres. Yet core accretion may not tell the whole story. Another possibility, known as disk instability, begins without slowly building a massive solid seed. Under suitable conditions, a dense region within the young disk could become gravitationally unstable and collapse rapidly, gathering gas into a giant planet almost directly. Researchers continue testing which process best explains Jupiter and Saturn, and whether both planets necessarily formed in the same way. Their chemistry preserves traces of that beginning. Hydrogen and helium dominate both giants, reflecting the composition of the ancient nebula, and more broadly, the material from which the Sun itself formed. Smaller quantities of heavier elements became incorporated during growth, leaving clues to where and how quickly each planet assembled. Jupiter's early arrival changed what could happen around it. Its growing gravity stirred nearby material, disrupting the orderly accumulation required to build another large planet in the region occupied today by the asteroid belt. Saturn added another massive gravitational influence farther outward. From there, the architecture became dynamic. Interactions between the giants, the remaining disk, and smaller developing worlds altered planetary orbits and redistributed material across immense distances. The solar system we see today was therefore shaped by motion as much as formation. Earth grew in an environment whose boundaries had already been influenced by two immense planets assembled millions of years earlier. There is a limit to how far machinery has physically entered Jupiter. The Galileo atmospheric probe crossed into its clouds in December 1995, transmitting measurements as it descended. Roughly 58 minutes later, communication ended. Its instruments had reached only about 95 miles beneath the cloud tops, an almost imperceptible distance within a planet roughly 86,881 miles across. Everything deeper must be reconstructed from evidence arriving indirectly. We cannot lower cameras toward Jupiter's center or drill through Saturn. Instead, scientists measure how these planets pull, rotate, vibrate, and generate magnetic fields. Each measurement responds to material hidden below, allowing researchers to infer structures that no instrument has touched. The National Aeronautics and Space Administration's Juno spacecraft transformed this process at Jupiter, entering orbit on July 4th, 2016. Juno repeatedly swept close to the planet, while radio tracking revealed minute changes in its motion. Those changes matter. Regions containing different amounts of mass exert slightly different gravitational pulls on the spacecraft. By measuring these variations with extraordinary precision, researchers can estimate how Jupiter's mass is distributed internally. More than 50 close orbital passages had been completed by 2024, gradually improving those models. Juno also measures the magnetic field, adding another window into material moving far beneath the visible atmosphere. Saturn required a different set of clues. The Cassini spacecraft orbited it from 2004 until 2017, accumulating 13 years of measurements. During its final phase, called the grand finale, Cassini completed 22 daring passages through the gap between Saturn and its innermost rings. Those trajectories placed the spacecraft where Saturn's gravitational influence could be measured with exceptional sensitivity. Cassini also mapped its magnetic environment, helping researchers constrain how material is arranged and moving within the planet. Yet Saturn offers another instrument, one that stretches around the planet itself. Its rings respond to vibrations originating deep inside Saturn. Internal oscillations slightly alter the planet's gravitational field, disturbing ring particles at particular locations. Researchers call this ring seismology. By studying wave patterns moving through the rings, they can work backward toward the oscillations that produced them, much as geologists use earthquake waves to investigate Earth's inaccessible interior. Jupiter also oscillates, although detecting those motions is considerably harder. Researchers have pursued Jovian seismology, studying subtle global vibrations that could provide another independent view beneath the clouds. None of these methods gives us a photograph. Instead, we have gravity, magnetism, orbital motion, atmospheric measurements, ring waves, and physics tested against computer models. When separate methods point toward the same internal arrangement, confidence grows. When they disagree, the model must change. In that way, you and I can explore places no spacecraft can survive, reading the interiors of giant planets through the effects they leave outside. On Earth, reaching the ground gives an atmosphere a natural ending. Jupiter offers no such boundary. If you descended through its clouds, there would be no shoreline between sky and planet, no sudden crossing into an interior. The atmosphere would simply become denser around you, with pressure replacing altitude as the more useful measure of depth. Scientists commonly define Jupiter's visible cloud level near a pressure of 1 atmosphere, comparable to Earth's pressure at sea level. Temperatures there hover around -234 degrees Fahrenheit. What appears through a telescope as colored stripes is actually the uppermost expression of an atmosphere extending thousands of miles downward. Ammonia ice crystals form the highest major cloud deck. Beneath them, changing pressure and temperature allow ammonium hydrosulfide clouds to develop. Deeper still comes a region where water can form clouds containing ice and liquid droplets. These layers overlap with powerful circulation, so the neat boundaries drawn in diagrams are far less orderly inside the planet itself. Across Jupiter, alternating bands are driven by jet streams flowing eastward and westward. Some reach speeds near 384 miles per hour. Their familiar appearance can make them seem like shallow weather patterns painted across a globe. Measurements from the Juno spacecraft indicate otherwise. The atmospheric circulation extends roughly 2,000 miles beneath the visible clouds, where increasing pressure gradually suppresses the organized winds. Saturn follows the same broad principle with its own extremes. Near its visible cloud tops, temperatures can fall near -285 degrees Fahrenheit. Ammonia ice again occupies the upper cloud region, while deeper chemistry changes as pressure and temperature rise. The winds move faster there. Around Saturn's equatorial regions, atmospheric currents can approach 1,100 miles per hour. Since there is no solid landscape beneath them, mountains and continents cannot interrupt their paths. Instead, planetary rotation, internal heat, pressure gradients, and fluid dynamics organize the atmosphere into persistent bands. As we move downward, familiar weather becomes increasingly difficult to separate from the planet beneath it. The active atmospheric region on these giants reaches immense depths, although its exact boundary depends on what property scientists measure. Organized winds weaken over thousands of miles while density continues increasing. Eventually, even the word atmosphere becomes incomplete. Hydrogen remains dominant, yet compression forces its molecules closer together. The material around you would steadily thicken as pressure climbed, without presenting any floor beneath your descent. This is where our everyday distinction between sky and world loses meaning. On Jupiter and Saturn, the visible atmosphere is simply the outer expression of a continuous planetary fluid, growing warmer, denser, and more compressed with depth. There is no surface waiting below the clouds. The sky itself becomes the planet. For nearly 2 centuries, astronomers have watched one immense oval drift across Jupiter. The Great Red Spot has persisted through generations of telescopes, spacecraft, and observers. Continuous records extend back to at least 1831. An earlier feature, seen in 1665, may have been the same storm, although that connection remains uncertain. The Great Red Spot is an anticyclone, meaning winds circulate around a region of high atmospheric pressure. In Jupiter's southern hemisphere, its circulation runs counterclockwise. Winds around the outer edge reach roughly 268 miles per hour, while the central region behaves more steadily. Its size has changed dramatically. During the 19th century, observations suggested a width exceeding 25,000 miles. Today, the storm measures roughly 9,800 miles across, still wide enough to span Earth. Measurements over decades show that it continues shrinking, although scientists cannot yet determine whether that process will eventually destroy it. Its depth was another mystery. Cloud images reveal only the upper structure, leaving researchers to estimate how far the circulation penetrates. Then, in July 2017, the Juno spacecraft passed directly above the Great Red Spot. At closest approach, it traveled roughly 5,600 miles above Jupiter's cloud tops. Juno's instruments revealed a storm extending far beneath its visible clouds. Later measurements indicated routes reaching roughly 200 miles downward. For something appearing almost two-dimensional from space, the Great Red Spot occupies an enormous volume of atmosphere. Its color remains harder to explain. Laboratory experiments and atmospheric models suggest sunlight can alter chemicals carried into the upper clouds, producing reddish compounds. Ammonia, sulfur-bearing molecules, and more complex organic chemistry may all contribute. Yet researchers still lack a single chemical explanation matching the exact colors observed across the storm. Jupiter also carries younger vortices. Oval B-A formed in 2000 when three smaller white storms merged. Over subsequent years, the resulting oval developed a reddish tint, earning the informal name Red Spot Jr. Watching that transformation gives scientists another natural experiment in Jovian atmospheric chemistry. Saturn produces giant storms differently, roughly once every Saturnian year, approximately 30 Earth years. A massive disturbance can erupt and spread around the planet. The most recent Great White Spot began in 2010, while Cassini watched its clouds expand until they formed a vast band around Saturn. These storms reveal how long atmospheric structures can survive without solid terrain beneath them. Jupiter's Great Red Spot has endured while its dimensions, winds, depth, and chemistry slowly evolve. We can watch its outer clouds from afar, yet the mechanisms sustaining such longevity remain only partly understood, preserved inside a vortex humanity has followed across centuries. At Saturn's North Pole, the atmosphere organizes itself into geometry. A six-sided current surrounds the polar region, its corners remaining recognizable while winds race through the pattern. Seen from above, the structure resembles something deliberately drawn across the clouds, yet its shape emerges entirely from moving fluid. The hexagon lies near 78 degrees north latitude. Each of its six sides stretches roughly 8,600 miles, slightly exceeding Earth's diameter. Nothing comparable has been observed as a persistent atmospheric structure on another planet. Saturn's South Pole offers no matching polygon. There, circulation forms a more conventional circular vortex. Voyager spacecraft observations revealed the northern feature during flybys in 1980 and 1981. Decades later, Cassini found it still present. That longevity showed researchers that the hexagon was more than a temporary arrangement of clouds. It is best understood as a standing wave, a wave pattern that remains fixed while fluid moves through it. Saturn's powerful eastward jet stream follows the six-sided boundary, maintaining the recognizable geometry as atmospheric material circulates. Laboratory experiments have reproduced similar polygons by rotating fluids at different speeds. Under particular conditions, circular flow naturally develops stable corners. Saturn provides those conditions on a planetary scale. The entire pattern rotates in roughly 10 hours, 39 minutes, and 23 seconds. Measuring Saturn's rotation is unusually difficult because there is no solid surface feature to follow. Atmospheric winds move at different speeds, while measurements tied to the magnetic field have introduced additional uncertainty. The hexagon, therefore, became one useful reference for studying the planet's deep rotation. Its appearance also changes with sunlight. When Cassini arrived in 2004, Saturn's northern hemisphere was emerging from winter, and the region inside the hexagon appeared distinctly blue. As northern summer approached, the interior gradually shifted toward golden tones. Researchers connect that transformation to seasonal photochemistry, as increasing sunlight produces hazes within the upper atmosphere. At the geometric center sits another structure entirely. A vast cyclone, roughly 1,250 miles wide, rotates around Saturn's pole. Its central eye is enormous, around 50 times wider than the typical eye of an earthly hurricane. Clouds circle its walls, while the surrounding hexagonal jet maintains a separate pattern farther outward. Measurements show that the hexagon extends at least about 60 miles beneath the visible cloud tops. Its full depth remains uncertain. What you see from above may therefore represent only the upper expression of a much deeper circulation system. We can reproduce polygonal waves in laboratories and describe the fluid mechanics that make them possible. Yet, Saturn has maintained this particular configuration across more than 4 decades of direct observation. Winds continuously move, seasons change, surrounding clouds evolve, and the six corners endure, held in place by an atmospheric balance that remains only partly understood. Imagine descending through Jupiter with an instrument that cannot be crushed. The familiar clouds recede above us, but nothing resembling ground appears below. Instead, every mile changes the material surrounding you. Pressure rises, temperature climbs, and hydrogen begins a transformation that makes ordinary ideas of atmosphere increasingly inadequate. Around 60 miles beneath the visible cloud tops, pressure reaches roughly 10 times Earth's sea level pressure. On Earth, a comparable pressure is found about 330 feet underwater. Yet, Jupiter's surroundings remain dominated by gases compressed far beyond anything we experience in open air. Temperatures near this level can approach 80 degrees Fahrenheit. This region overlaps with Jupiter's deeper water clouds. Here, conditions allow water droplets to exist within an atmosphere also containing hydrogen, helium, ammonia, and other compounds. The Galileo probe entered Jupiter on December 7, 1995, and sampled part of this environment directly. Its measurements initially created a puzzle. Scientists expected considerably more water. Galileo had entered an unusual atmospheric region called a hotspot, where descending air produces unusually dry conditions. The probe therefore sampled a location that was not representative of Jupiter as a whole. Its limited path became an important reminder of scale. Measuring one column through Jupiter can resemble sampling one narrow patch of Earth's weather and trying to infer an entire planet. Below that region, compression becomes the dominant story. Hydrogen molecules are forced progressively closer together. Density increases continuously, and the surrounding material begins behaving less like the gases we know near Earth's surface. There is still no boundary to cross. At roughly 430 miles beneath the cloud tops, pressure can approach 1,000 times Earth's atmospheric pressure. Hydrogen has become extraordinarily dense here. Its behavior increasingly resembles a fluid, even though there is no distinct ocean surface marking where that change occurred. Continue towards 600 miles, and temperatures rise beyond 1,700 degrees Fahrenheit. Pressure and heat now push hydrogen into conditions where the usual separation between gas and liquid loses usefulness. Scientists describe this state as a supercritical fluid, meaning matter existing above the pressure and temperature where separate gas and liquid phases can remain distinct. You could descend through this transition without encountering a recognizable surface. Around you, hydrogen would simply become denser, hotter, and increasingly fluid-like. The change happens continuously. Gravity would also change gradually during the descent, shaped by Jupiter's rotation and the enormous mass still lying beneath us. After 600 miles, we would still have crossed only a small fraction of Jupiter's immense radius. Yet ordinary atmospheric language is already beginning to fail. What started above as recognizable weather has become compressed planetary material, and the distinction between atmosphere and interior is now something physics defines more clearly than sight. Hydrogen is supposed to be simple. A single proton and a single electron make the most abundant element in the universe. Yet deep inside Jupiter, immense pressure forces hydrogen into a form so unfamiliar that it behaves like a metal. Around 8,700 miles beneath Jupiter's cloud tops, pressure approaches 1 million times Earth's atmospheric pressure. Hydrogen molecules can no longer preserve their ordinary structure. The electrons that normally remain associated with individual atoms become mobile, moving through the compressed material with far greater freedom. Electrical current can then flow through it efficiently. Physicists call this state metallic hydrogen. The idea predates the spacecraft age. In 1935, physicists Eugene Wigner and Hillard Bell Huntington calculated that sufficiently compressed hydrogen should undergo a transition into a metallic state. Their prediction created an extraordinary experimental challenge. Reproducing planetary pressures on Earth requires concentrating enormous force onto samples scarcely visible to the eye. Diamond anvil cells provide one method. Two carefully shaped diamonds squeeze a tiny hydrogen sample between their tips, exploiting diamond's exceptional hardness. In 2017, researchers at Harvard University reported producing metallic hydrogen under extreme compression. The claim generated substantial scientific debate, illustrating how difficult the state is to create, preserve, and verify experimentally. Jupiter does the experiment continuously. Its metallic hydrogen region is thought to extend for tens of thousands of miles through the deep interior. Unlike a rigid piece of metal, this material exists as an intensely hot, compressed fluid. As Jupiter rotates, electrically conducting hydrogen moves through the planet. Those motions sustain a dynamo, the process in which moving conductive material generates a planetary magnetic field. That connection gives us evidence from far outside Jupiter. The planet possesses the strongest planetary magnetic field in our solar system. Its vast magnetic environment stretches millions of miles through space. If that surrounding magnetic structure could somehow glow visibly from Earth, its apparent width would span several times that of the full moon. Saturn contains metallic hydrogen as well, though its lower mass changes where the transition occurs. Pressures rise more gradually there, so models generally place the metallic region deeper inside Saturn than Jupiter, beginning thousands of miles farther beneath the visible atmosphere. Yet Saturn adds another puzzle. Its magnetic field lies almost perfectly along its rotational axis. Fields generated by planetary dynamos usually show some measurable tilt, making Saturn's alignment unusually precise. So the simplest element becomes one of the giant's most consequential materials. Under pressures we can barely reproduce. Hydrogen gains electrical properties associated with metals while remaining part of a flowing planetary interior. We cannot retrieve a sample from Jupiter. We infer its presence through laboratory physics, gravitational models, and the enormous magnetic field produced by motion deep beneath the clouds. Planetary magnetic fields rarely point exactly where their planets spin. Earth's magnetic axis is tilted about 11 degrees from its rotational axis. Jupiter's differs by roughly 10 degrees. Uranus reaches an extraordinary 59 degrees. These offsets are expected consequences of turbulent electrical currents moving through planetary interiors. Saturn refuses to cooperate. Measurements place its magnetic axis within less than 0.06 degrees of its rotation axis. The alignment is so precise that determining the remaining tilt has challenged spacecraft instruments. From outside, Saturn appears to possess an almost perfectly symmetrical magnetic field centered on its spin. That creates a problem for dynamo theory, the physics describing how moving electrically conductive fluids sustain planetary magnetism. A dynamo depends on complex circulation within the conducting interior. Perfect axial symmetry creates mathematical difficulties because a completely symmetrical field should struggle to maintain itself through the standard dynamo process. Yet Saturn clearly has one. One possibility is that the magnetic field we measure is being altered before reaching space. Deep inside, the true dynamo may possess more asymmetry than Cassini observed. Above that generating region, researchers have proposed a layer whose electrical conductivity and rotation differ from the fluid beneath it. Helium could be central to this arrangement. Under Saturn's immense internal pressures, helium can separate from hydrogen and migrate inward. This redistribution may create composition gradients, meaning neighboring layers contain different proportions of material. Such gradients can suppress large-scale convection and produce a relatively stable layer above the deeper dynamo. If that layer conducts electricity weakly enough, magnetic structures passing through it could become smoothed. Smaller irregularities would fade with distance, leaving a more symmetrical field at the cloud tops. What you measure outside Saturn might therefore be a filtered version of something more complicated below. Cassini tested that possibility with extraordinary precision during its grand finale in 2017. The spacecraft repeatedly passed between Saturn and its rings, obtaining magnetic measurements closer to the planet than previous missions. The expected measurable tilt never emerged. Saturn remained astonishingly aligned, but Cassini detected smaller variations and oscillations within the field. These subtle structures indicate that Saturn's magnetism is not perfectly simple. They preserve hints of deeper motions whose geometry remains difficult to reconstruct. The uncertainty even complicated attempts to determine Saturn's day. Scientists often estimate a giant planet's rotation from periodic changes in its magnetic field. Saturn's near symmetry removes the obvious rotating marker, contributing to decades of disagreement over its precise internal rotation period. We therefore know Saturn possesses a functioning dynamo, probably driven with an electrically conducting hydrogen. We can measure its field with remarkable accuracy. What remains unresolved is how an active, moving interior produces magnetism aligned so precisely with the planet's rotation. Saturn obeys electromagnetism, yet its internal arrangement has found a configuration of our simplest planetary models still struggle to reproduce. Saturn is losing helium from the atmosphere we can observe, yet the element has not escaped the planet. Instead, much of it appears to be migrating inward, falling through layers of hydrogen under conditions found nowhere naturally accessible on Earth. The result is planetary rainfall without clouds, water, or a recognizable sky. When Saturn formed, its proportions of hydrogen and helium were broadly similar to the Sun's. By mass, the original mixture contained roughly 75% hydrogen and 25% helium. Measurements of Saturn's upper atmosphere, however, indicate that helium is now depleted there. Something inside the planet has been separating the two elements. That separation developed as Saturn cooled over roughly 4,500,000,000 years. Under particular combinations of pressure and temperature, helium becomes increasingly difficult to dissolve within dense hydrogen. Physicists call this helium immiscibility, meaning the two substances can no longer remain completely mixed. Tiny regions rich in helium can then gather into droplets. Gravity carries them deeper. The process is known as helium differentiation. As each droplet descends, gravitational potential energy is converted into heat, multiplied across an entire planet, and sustained for immense periods. That falling material provides a substantial internal energy source. Saturn needs one. The planet radiates roughly twice as much energy into space as it receives from sunlight. Simple cooling left over from its formation cannot fully account for that excess. Helium separation provides an important part of the explanation, allowing Saturn to remain warmer internally than simpler evolutionary models predicted. The rain also changes Saturn's composition with depth. Upper layers gradually lose helium, while deeper regions become enriched. Instead of remaining chemically uniform, the planet slowly sorts some of its material, according to how hydrogen and helium behave under extreme pressure. Neon may join the descent. Models suggest neon can dissolve preferentially into helium-rich droplets, allowing it to be transported inward as the helium falls. Measurements of giant planet atmospheres show unusual, noble gas abundances that researchers use to test these interior models. Jupiter experiences related physics, though its greater mass and hotter interior change the conditions. Helium separation appears to occur there as well, but Saturn's cooler interior allows the process to become especially important for its thermal evolution. If you could follow one helium droplet, there would be no brief fall ending against a surface. It would move inward through dense hydrogen, joining progressively deeper material while releasing energy along the way. Across billions of years, countless such droplets reshape Saturn from within. We see their consequences indirectly through atmospheric composition, internal heat, and planetary evolution. The rain itself remains buried beneath thousands of miles of opaque fluid, continuously redistributing one of the simplest elements in the universe through one of its largest worlds. A carbon atom entering Saturn's deeper atmosphere may eventually encounter conditions where its chemistry changes completely. Methane supplies the starting material. As pressure and temperature rise, methane molecules can break apart, freeing carbon that may reorganize into one of nature's hardest structures, diamond. Physicist Marvin Ross proposed this possibility in 1981. His calculations suggested that conditions inside giant planets could force carbon out of hydrocarbon mixtures and into dense, solid phases. Under suitable pressures, carbon atoms favor the tightly bonded crystal arrangement found in diamond. The process would begin far below any visible cloud. Carbon released from methane could gather into tiny particles. As more atoms joined the crystal structure, those particles might grow and descend under gravity, passing through increasingly dense planetary material. This would be diamond rain in a literal physical sense. Saturn appears especially favorable because its internal temperature profile may allow solid diamond to survive across part of the descent. Estimates presented in 2013 suggested that the planet could potentially produce around 2,200,000 pounds of diamond each year. That figure depends strongly on models of carbon abundance, chemistry, temperature, and circulation, so it should be treated as an estimate rather than a measured production rate. Deeper down, survival becomes harder. Temperatures eventually rise enough for diamond to melt under the pressures involved. The falling crystals could therefore transform into liquid carbon before reaching the deepest interior. That material might dissolve into surrounding fluids, mix with heavier material, or contribute to carbon-enriched regions whose exact structure remains uncertain. Jupiter presents a different environment. Its greater internal heat may prevent solid diamonds from surviving as long within the relevant pressure range. Carbon could still pass through diamond-forming conditions, but any crystals would likely melt sooner than comparable material inside Saturn. Laboratory experiments give the hypothesis a physical foundation. Researchers, using powerful laser pulses, have compressed hydrocarbon materials for incredibly brief periods, creating pressures resembling those inside giant planets. Experiments at the Stanford Linear Accelerator Center, National Accelerator Laboratory, have observed nanodiamonds, crystals only billionths of a yard across, forming under conditions especially relevant to Uranus and Neptune. Gas giants follow different pressure and temperature paths, so those results do not prove diamonds are falling inside Saturn. That distinction matters. No spacecraft has detected Saturnian diamonds, and none has sampled the depths where they might form. What we have instead is a chain of evidence: known carbon chemistry, high-pressure experiments, planetary interior models, and calculations describing how methane behaves under compression. So when we picture diamonds falling through Saturn, we are describing a scientifically plausible hypothesis rather than an observed fact. The crystals remain unseen, their existence inferred from physics operating beneath layers no instrument has reached. Deep within Jupiter, the word ocean takes on an unfamiliar meaning. There is no water, shoreline, or open surface. Instead, hydrogen itself forms an immense electrically conducting fluid, occupying a substantial fraction of the planet and moving continuously under pressures beyond ordinary experience. This region develops as hydrogen changes under compression. Far above, its molecules retain familiar paired structures. Deeper inside, pressure forces electrons away from those molecular bonds. The transition into metallic behavior occurs gradually across a broad region rather than along a clean boundary. That matters because Jupiter is hot enough for its deep hydrogen to remain fluid. At pressures reaching millions of times Earth's atmospheric pressure, temperatures climb beyond 18,000 degrees Fahrenheit. The resulting material behaves as a dense, conducting liquid whose electrical properties resemble those of metals. Its dimensions are planetary. The metallic hydrogen region extends across tens of thousands of miles, surrounding Jupiter's deeper interior. Calling it an ocean helps describe its fluid behavior, although no vessel could float upon it. There is no upper surface where one material suddenly ends and another begins. Instead, molecular and metallic forms can coexist across a transitional zone. Pressure steadily changes their proportions with depth. If you could move through this region, the electrical character of the surrounding hydrogen would strengthen progressively, while its density and temperature continued rising. Movement within this vast fluid is crucial. Jupiter still releases internal heat, and that energy helps drive convection, the circulation created when warmer material rises while cooler material sinks. Rotation organizes these currents into complex patterns spanning enormous distances. Because metallic hydrogen conducts electricity, its motion also transports electrical charge. Those moving charges sustain Jupiter's magnetic dynamo. The magnetic field detected above the clouds therefore carries information about circulation occurring thousands of miles below. Juno measurements have shown that this field is unexpectedly uneven. One especially intense region lies near Jupiter's equator, while the northern and southern magnetic structures differ substantially. Researchers sometimes call the concentrated equatorial feature the Great Blue Spot, although the name describes magnetic intensity rather than visible color. Such asymmetry suggests that the dynamo may operate within particular depths or through irregular convection patterns. Scientists compare these magnetic measurements with computer simulations, testing which internal flows can reproduce the field observed outside. Saturn contains a comparable conducting fluid region, but its smaller mass produces different pressure conditions. Metallic hydrogen occupies a smaller proportion of Saturn's interior and develops deeper beneath its clouds. Within Jupiter, however, this immense fluid reservoir dominates much of the hidden planet. We cannot see its currents directly. Their presence appears through heat, transport, gravity, and magnetism, allowing us to trace the behavior of an ocean whose waves are movements of compressed hydrogen itself. For generations, planetary scientists gave Jupiter a center that looked reassuringly familiar. Beneath its immense hydrogen interior, models placed a compact core of rock and ice. Estimates commonly gave that core between 10 and 15 Earth masses. It provided a tidy foundation for explaining how the planet formed. Then Juno measured Jupiter's gravity with extraordinary precision. As the spacecraft passed around the planet, tiny changes in its motion revealed how mass was distributed far below the visible atmosphere. Those measurements produced an interior that resisted the older picture. Jupiter's deepest heavy material appeared spread across a much larger volume. By 2021, analyses published in the journal Nature were refining a radically different structure. Instead of ending at a distinct boundary, Jupiter's core region may extend outward through roughly 40% of the planet's radius. That places core material across tens of thousands of miles. Scientists call this a fuzzy or dilute core. The name describes a broad mixture rather than a compact sphere. Heavy elements associated with rock, iron, and planetary ices become increasingly mixed with hydrogen and helium as you move outward. Their concentration changes gradually. So where does Jupiter's core actually end? Current models cannot draw a simple line. Depending on how the interior is defined, estimates vary substantially. The entire enriched region may contain roughly 25 to 45 Earth masses of heavy elements, although its precise composition remains uncertain. One explanation reaches back to Jupiter's violent youth. Computer simulations suggest that a developing planet around 10 times Earth's mass could have collided with the young giant. A sufficiently energetic impact might disrupt an originally compact core and distribute heavy material throughout the surrounding interior. The geometry matters. Simulations indicate that both direct and oblique collisions can produce extensive mixing under suitable conditions. Jupiter would then preserve evidence of that ancient encounter within its present density gradient. Yet a giant impact is not the only possibility. Slow mixing during formation and later interior evolution may also help create a dilute core. Saturn has complicated the story further. Cassini never entered its deep interior, yet Saturn's rings recorded vibrations linked to motions within the planet. Ring seismology allows researchers to interpret those patterns, much as geophysicists use seismic waves to study Earth's interior. Results published in 2021 indicated that Saturn also possesses an extended core region. Models suggest heavy elements remain distributed across roughly 60% of Saturn's radius. The concentration increases inward rather than suddenly reaching a solid boundary. Both planets, therefore, challenge the simple layered diagrams we once used. Their deepest regions appear chemically graded, with materials blending across enormous distances. At Jupiter and Saturn's centers, the distinction between core and surrounding envelope becomes a matter of changing concentration rather than a clearly defined surface. A collision capable of reshaping Jupiter would have required another enormous world. During the solar system's first few million years, such bodies were still forming around the young Sunday. They were protoplanets, planetary embryos whose growth had begun but whose final orbits and fates remained unsettled. Some reached several Earth masses. One may have crossed Jupiter's path. For Jupiter's diffuse core, simulations favor an impactor of at least 10 Earth masses. That means a world substantially heavier than Earth entered a collision course with the growing giant. The timing would have been early, probably within the first 3 to 5 million years, while Jupiter itself was still assembling. Such an encounter fits a solar system that was dynamically restless. One influential framework, called the Grand Tack Model, proposes that Jupiter migrated substantially after forming. Interactions with the surrounding disk of gas could have carried it inward toward the region of today's asteroid belt. Later, after Saturn became involved in the orbital dynamics, Jupiter's migration may have reversed and carried both giants outward. That movement would have disturbed nearby material profoundly. Planetary embryos could be scattered onto new trajectories, sometimes crossing the paths of larger worlds. In such an environment, a massive collision becomes physically plausible rather than an isolated accident. Researchers at Rice University explored this possibility in computer simulations published in 2019. Their models tested a protoplanet around 10 Earth masses striking young Jupiter. For a nearly head-on collision, impact speeds around 15 to 30 miles per second could drive the intruding body deep into Jupiter. There would be no surviving planet afterward. The impactor would be shredded, heated, and absorbed. Its heavy elements could mix outward through Jupiter's original core region, producing a broad distribution resembling the structure inferred from Juno's gravity measurements. Timing changes the result. A younger Jupiter, still developing internally, could mix the incoming material more efficiently. Later impacts encounter a more established interior, making extensive redistribution harder. Collision angle matters too. An oblique strike deposits energy and material differently from a direct hit, leaving another internal pattern. As gravity measurements improve and interior models become more precise, scientists can compare those predicted patterns against Jupiter's actual mass distribution. We are effectively examining a scar without seeing the original wound. Saturn offers an intriguing parallel. Its own diffuse core could reflect violent early evolution, although present evidence does not identify a comparable impact with the same confidence. If Jupiter carries this ancient collision inside it, then a vanished protoplanet remains physically incorporated into the giant today. you cannot point to its fragments in space. Its possible signature survives instead as heavy material dispersed through Jupiter's depths, preserved for more than 4 billion years inside the architecture of the planet itself. Far beyond Jupiter's clouds, the planet continues to exert control through magnetism. Its magnetic domain, called the magnetosphere, is the region where Jupiter's field dominates the behavior of charged particles around it. Facing the Sun, this immense structure reaches roughly 600,000 miles outward. Behind Jupiter, the magnetic tail can extend more than 4 million miles into space. Its apparent scale becomes stranger from Earth. If our eyes could see the entire magnetosphere, it would span roughly 5 times the width of the full moon. Jupiter itself remains hundreds of millions of miles away, ranging from roughly 365 million to 600 million miles from Earth as the planets move around the Sunday. The source lies deep inside Jupiter. Rotating, convecting metallic hydrogen conducts electrical current, sustaining a planetary dynamo. Earth produces its magnetic field through motion in a liquid iron outer core. Jupiter accomplishes something similar using hydrogen transformed by enormous pressure into an electrically conducting fluid. Yet the resulting field is unusually complicated. Near Jupiter's cloud tops, its average strength is roughly 20 times Earth's surface magnetic field. Local regions can become much stronger. Measurements by the Juno spacecraft have revealed intense concentrations exceeding 20 Gauss, a unit describing magnetic field strength. The pattern is asymmetric as well. Jupiter's northern and southern magnetic structures differ substantially, reflecting complex processes within the dynamo region. One remarkable concentration near the equator has been nicknamed the Great Blue Spot. Despite its name, it has nothing to do with visible color. It marks an unusually concentrated patch of magnetic flux detected through Juno's instruments. Charged particles become caught within this enormous magnetic environment. Electrons and protons spiral along field lines, while interactions near the poles generate immense auroras. Much of their energy emerges in ultraviolet and X-ray wavelengths, beyond what your eyes can naturally detect. These emissions can persist even when solar activity changes, because Jupiter has another powerful particle source nearby. That source is Io, the innermost of Jupiter's 4 large Galilean moons. Io's volcanoes continually release sulfur dioxide. Once that material escapes into space, sunlight and energetic particles strip electrons from atoms and molecules, creating electrically charged material called plasma. Jupiter's rapid rotation sweeps this plasma around the planet, forming the Io plasma torus, a vast donut-shaped ring glowing strongly in ultraviolet wavelengths. Io itself remains electrically linked to Jupiter through a magnetic flux tube. This connection behaves like a gigantic circuit, carrying roughly 2 trillion watts of power between the Moon and Jupiter's magnetic environment. Through that circuit, a volcanic moon becomes part of a planetary electromagnetic system. Jupiter's magnetosphere is therefore more than an invisible shield surrounding the planet. It is an active environment where deep interior motion, charged particles, volcanic material, radiation, and orbiting moons remain physically connected across millions of miles. Io travels through a gravitational environment that never allows its interior to settle. Orbiting roughly 262,000 miles above Jupiter's cloud tops, this moon remains separate from the planet, yet Jupiter continuously reaches into it through gravity. The result is a world whose geology is driven by orbital motion. More than 400 active volcanic regions have been identified across Io, Some eruptions send sulfur dioxide plumes nearly 300 miles above the surface. Against the blackness of space, these fountains rise far beyond the heights reached by terrestrial volcanoes, then spread outward before material falls back across the moon. Their energy comes from tidal heating. This is heat produced when changing gravitational forces repeatedly deform a world. Io follows a slightly elliptical orbit, maintained partly through gravitational interactions with Europa and Ganymede. As its distance from Jupiter changes, the strength of Jupiter's pull changes too. The moon flexes continuously. Rock inside Io bends under this repeated distortion, generating frictional heat throughout its interior. Estimates place the resulting power near 100 trillion watts. On Earth, radioactive decay contributes greatly to internal heating. On Io, gravitational flexing dominates the volcanic engine. You can see the consequences at Loki Patera, Io's largest volcanic depression. It spans roughly 127 miles and contains an enormous lava lake. Observations indicate that sections of its surface periodically overturn. Cooled crust becomes unstable and sinks, exposing hotter molten material beneath. This resurfacing can propagate across the lake over time. A major repeating cycle has been observed on a timescale of roughly 540 days. Although Loki's behavior varies, the feature becomes a natural laboratory where astronomers can watch planetary volcanism evolve across an entire basin. Across Io as a whole, volcanic material accumulates rapidly. An average resurfacing rate near 4/100ths of an inch per year may sound modest. Spread across an entire moon, it is extraordinary. Over a few million years, enough material can accumulate to replace the visible surface and erase ancient impact craters. Io also releases heat far faster than Earth. Its average heat flow per unit area is roughly 30 times greater, reflecting the enormous energy continually generated inside. Instead of preserving an old, cratered landscape, Io repeatedly covers itself with lava and sulfur-rich deposits. That activity extends beyond geology. Sulfur dioxide, escaping from volcanic plumes, enters Jupiter's magnetic environment, where energetic processes ionize the material, stripping electrons away and creating plasma. Jupiter's rotation then carries those charged particles around the planet. So when we observe Io erupting, we are watching gravity become heat, heat become volcanism, and volcanism become charged material in space. A moon only a fraction of Jupiter's size becomes part of a system, spanning hundreds of thousands of miles, linking orbital resonance, molten rock, volcanic gases, and Jupiter's immense magnetic domain. Europa carries its ocean beneath a surface that records stress rather than age. Long fractures cross the moon's water ice, intersecting ridges and disrupted plains across a shell repeatedly reshaped by forces below. From orbit, the pattern resembles a crust that has been pulled, shifted, and refrozen many times. Beneath that exterior, evidence points toward a global liquid water ocean. Estimates suggest it may hold roughly twice as much liquid water as all Earth's oceans combined. Jupiter supplies the mechanism that helps keep it from freezing completely. Its gravity repeatedly flexes Europa as the moon follows an orbit shaped by resonance with neighboring moons, producing tidal heating inside. The ice above this ocean may be only 6 to 19 miles thick. Below it, the water could descend another 60 to 100 miles. That gives Europa an extraordinary internal arrangement, with a comparatively thin, frozen exterior covering a deep planetary ocean. We cannot see that water directly, yet the surface provides clues. The Hubble Space Telescope has reported observations consistent with water vapor plumes rising above Europa, although their existence and frequency remain debated. If such plumes truly originate from the buried ocean or shallow reservoirs, material from beneath the ice may occasionally reach space. That possibility changes how scientists can investigate Europa. Instead of drilling through miles of ice, a spacecraft might pass through expelled material and analyze its chemistry. You could effectively sample part of an inaccessible environment while remaining above the surface. The ocean's lower boundary matters just as much. Current models indicate that liquid water probably contacts Europa's rocky mantle. On Earth, interactions between rock and seawater can release chemical energy, especially around hydrothermal systems on the ocean floor. Such reactions provide ingredients and energy gradients that living systems can exploit. Europa also receives intense radiation from Jupiter's magnetic environment. Radiation striking surface ice creates oxidants, chemically reactive compounds containing oxygen. For these materials to influence the deeper ocean, some process must transport them downward through the ice. Scientists still debate how efficiently that exchange occurs. The Europa Clipper mission was launched by the National Aeronautics and Space Administration in October 2024. It is traveling toward Jupiter for arrival in 2030, then will perform roughly 49 close flybys of Europa. Instruments will examine the ice shell, interior ocean, surface chemistry, geology, and surrounding space. Each flyby approaches the same fundamental problem from a different angle. Gravity measurements can constrain the moon's internal structure. Radar can probe portions of the ice. Magnetic observations can reveal properties of the conductive ocean beneath. Europa, therefore, gives us another expression of Jupiter's influence. The same immense planetary mass that governs the surrounding system also helps maintain liquid water inside a frozen moon, hundreds of millions of miles from the Sunday. Two moons in Jupiter's outer system carry histories written in very different ways. Ganymede has been internally active enough to build a magnetic environment of its own. Callisto has preserved an ancient exterior that barely seems altered by time. Ganymede measures about 3,273 miles across, making it the largest moon in the solar system. It is even wider than Mercury. Yet its planetary character reaches much deeper than size. Ganymede is the only known moon that generates an intrinsic magnetic field, produced by motion within a liquid iron core. That field creates a small magnetosphere embedded inside Jupiter's enormous one. The interaction forms a layered magnetic environment unlike anything surrounding another moon. When Juno passed Ganymede in June 2021, it made the closest spacecraft approach in more than 2 decades. Measurements refined our understanding of the moon's magnetic surroundings, while instruments examined water ice across its surface. Far below that ice, another hidden structure probably exists. Evidence indicates that Ganymede contains a deep saltwater ocean, possibly divided by multiple layers of high-pressure ice. Dissolved salts lower the water's freezing point, helping liquid persist under conditions where pure water would freeze more readily. Jupiter's gravity also supplies tidal stresses, although Ganymede experiences far less extreme deformation than Europa. Travel farther outward, and the landscape changes completely. Callisto occupies the most distant orbit among the 4 large Galilean moons. Its surface is densely packed with impact scars, preserving events that occurred more than 4 billion years ago. Geological resurfacing has been limited compared with Io or Europa. Ancient craters, therefore, remains stacked across terrain that records the violent early solar system. But Callisto may conceal liquid water too. During flybys by the Galileo spacecraft, scientists measured how the moon responded to Jupiter's changing magnetic field. The response was consistent with an electrically conducting layer beneath the crust. A global ocean containing dissolved salts provides one of the strongest explanations. These worlds have been connected in human history since January 1610. Galileo Galilei observed Io, Europa, Ganymede, and Callisto moving around Jupiter. Their motion demonstrated that celestial bodies could orbit something other than Earth. You can imagine how directly that observation challenged a cosmos arranged entirely around our world. Today, we are returning with instruments Galileo Galilei could never have envisioned. The European Space Agency launched the Jupiter Icy Moons Explorer in April 2023. Its mission will investigate Europa, Callisto, and Ganymede after reaching the Jovian system. In 2034, the spacecraft is planned to enter orbit around Ganymede, becoming the first spacecraft to orbit any moon beyond Earth's own. Together, Ganymede and Callisto preserve two complementary records, one written through internal differentiation and magnetism, the other through impacts left largely undisturbed across immense stretches of time. A sheet of ice can stretch across an enormous distance while remaining astonishingly thin. Saturn's rings do exactly that. From their inner reaches to their outer edge, the main ring system spans roughly 175,000 miles. Yet across many regions, its vertical thickness averages only about 30 feet. The material itself is mostly water ice. Individual particles range from grains smaller than sand to fragments comparable in size to houses. Rocky material and dust contribute a smaller fraction. Each piece follows its own orbit around Saturn, collectively producing the broad, luminous bands we recognize from afar. Their scale suggests enormous mass, but appearances mislead. Combined, the rings contain only around 40% of the mass of Saturn's moon Mimas. That is roughly 0.4% of the mass of Earth's moon. The rings are therefore immense in area, while surprisingly sparse in material. Their age is even more revealing. Measurements gathered during Cassini's grand finale helped scientists estimate ring mass with unprecedented precision. Research, published in 2023, supported an age between roughly 100 million and 400 million years. If that estimate is correct, dinosaurs already inhabited Earth when Saturn acquired the rings we see today. One explanation begins with a lost moon. A satellite perhaps comparable to Mimas, or somewhat larger, may have migrated dangerously close to Saturn. Eventually it crossed the Roche limit, the distance where Saturn's tidal forces can overpower the moon's own gravity. The satellite was torn apart. Its fragments spread into orbit, collided repeatedly, and gradually flattened into a disk. But the resulting structure is temporary. Saturn is steadily reclaiming its rings. Ice particles near the inner regions become influenced by gravity and electromagnetic forces, directing material downward into the planet. Scientists call this process ring rain. Estimates suggest Saturn may receive between roughly 880 and 6,200 pounds of ring material every second. Cassini detected consequences within Saturn's upper atmosphere. Incoming ring material changes local chemistry, creating identifiable atmospheric footprints where particles descend. The rings and planet are therefore exchanging matter continuously, linking an orbital structure hundreds of thousands of miles wide with processes occurring inside Saturn's atmosphere. At estimated present loss rates, much of the ring system could disappear within roughly 100 million years. That timescale is substantial to us, yet brief compared with Saturn's age of more than 4 billion years. So when you look at Saturn's rings, you are seeing a planetary feature during a limited chapter of its existence. We happen to live while the fragments remain spread around Saturn, bright enough to transform the planet's appearance, while every passing second carries a little more of that ancient broken moon downward. Rain falls on Titan. Rivers carry it across the landscape. Lakes collect it in broad basins. Clouds gather overhead, and seasons reshape the weather. Yet the liquid moving through this familiar cycle is methane, flowing across a world chilled to roughly 290 degrees below 0 Fahrenheit. Titan is Saturn's largest moon and the only moon surrounded by a dense atmosphere. Nitrogen dominates the air, while methane and other compounds create a thick orange haze. At the surface, atmospheric pressure reaches about 1.45 times Earth's sea level pressure. The atmosphere itself is roughly 1.5 times denser. A human standing there would therefore face an unusual problem. Pressure would not require a bulky pressure suit. You would still need breathable air and extraordinary protection from the cold. Around you, methane would perform many roles that water performs on Earth. Sunlight drives evaporation from lakes and damp surfaces. Methane enters the atmosphere, condenses into clouds, then returns as rain. Flowing liquid carves channels through Titan's terrain before collecting in polar lakes and seas. This is a complete hydrological style cycle built from different chemistry. The greatest reservoirs cluster around the northern pole. Kraken Mare is the largest known sea there, covering approximately 154,000 square miles. Liquid methane and ethane fill its basins, producing coastlines and channels that spacecraft images reveal beneath Titan's atmospheric haze. We have already reached this distant ground once. On January 14th, 2005, the Huygens probe separated from the Cassini mission and descended through Titan's atmosphere. Its cameras watched the landscape emerge beneath the haze before the probe landed on a broad plain. Huygens survived for 72 minutes on the surface. Images revealed rounded pieces of water ice scattered across the ground. Their shapes suggested erosion and transport by flowing liquid, evidence that methane had repeatedly altered the terrain. Titan also appears to hide another liquid environment far below. Measurements of its gravity, rotation, and deformation support the presence of a subsurface ocean beneath the icy crust. That buried reservoir is thought to contain liquid water, creating a layered world where hydrocarbons flow above while water remains deep underground. Such chemistry makes Titan especially valuable for studying habitability and complex organic reactions. Methane, nitrogen, sunlight, and atmospheric chemistry continually manufacture carbon-rich molecules that settle onto the surface. The National Aeronautics and Space Administration plans to investigate those materials with Dragonfly, a nuclear-powered rotorcraft designed to fly between multiple locations. Its launch is planned for 2028, with arrival at Titan expected in 2034. Instead of remaining at one landing site, Dragonfly will cross the landscape, sampling organic chemistry in different environments. From beneath Titan's orange atmosphere, Saturn would hang beyond a world where weather continues without liquid water at the surface, following familiar patterns through profoundly unfamiliar chemistry. At only 313 miles across, Enceladus could disappear inside the scale of many larger moons. Its modest size once suggested a frozen body with little geological activity. Then, in 2005, Cassini observed material erupting from its south polar terrain, revealing an interior far more active than its dimensions implied. Jets were streaming directly into space. Water vapor and ice particles escaped alongside carbon-bearing compounds, with some material traveling around 800 miles per hour. The eruptions emerge mainly through long fractures near the South Pole, where internal heat keeps portions of the icy crust unusually active. Cassini returned repeatedly, eventually making 23 close encounters with Enceladus during its mission. Some trajectories carried the spacecraft directly through plume material. This allowed its instruments to analyze particles originating beneath the surface without drilling through the ice. Those measurements transformed our picture of the moon. Gravity data and other observations showed that liquid water exists beneath the crust, now understood as a global subsurface ocean. The south polar fractures provide pathways connecting that buried water with space. Inside sampled plume material, Cassini detected hydrogen gas, carbon dioxide, methane, salts, and complex organic molecules. Some of those organic compounds contain chemical structures related to the building blocks used in amino acids. None of this demonstrates biology. It does show that Enceladus contains water, organic chemistry, and an accessible source of chemical energy. Hydrogen provided an especially important clue. Scientists concluded that it could be produced through reactions between liquid water and warm rock on the ocean floor. Such hydrothermal activity occurs when heated water circulates through rocky material, driving chemical reactions that release energy. On Earth, comparable processes support ecosystems around deep ocean hydrothermal vents, where organisms survive without energy from sunlight. Enceladus therefore offers a natural environment where several ingredients associated with habitability may coexist beneath an icy exterior. The escaping ocean also changes Saturn's surroundings. Material leaving Enceladus spreads along its orbit and supplies Saturn's E ring, a broad, diffuse ring composed largely of microscopic ice particles. We are effectively seeing material from an underground ocean distributed across space around the planet. What keeps such a small moon warm enough? Its orbit provides much of the answer. Enceladus participates in an orbital resonance with Dione. For every orbit completed by Dione, Enceladus completes two. Repeated gravitational stresses flex the smaller moon, producing internal friction and heat that help maintain liquid water. That accessibility makes Enceladus unusual among ocean worlds. Its buried reservoir naturally delivers samples beyond the crust, where spacecraft can collect them. One proposed mission, Enceladus Orbalander, would combine prolonged orbital observations with a surface landing. Rather than forcing machinery miles through ice, such a spacecraft could examine material that Enceladus itself has already carried upward from its hidden ocean. The history of the solar system survives inside its largest planets. Jupiter and Saturn preserve material gathered when the sun was young, before the planetary arrangement we recognize had fully emerged. Their interiors therefore function as records of conditions more than 4 billion years ago. One clue comes from heavy elements, meaning material heavier than hydrogen and helium. Their abundance inside Jupiter reveals how much rock and ice existed near the giant planet while it formed. Those ingredients came from the solar nebula, the broad disk of gas and dust surrounding the newborn Sunday. Their distribution matters too. Jupiter's diffuse core indicates that heavy material became mixed across a vast interior region. The evidence is consistent with an early collision involving a large protoplanet. Such an encounter places substantial planetary bodies near Jupiter within the first few million years of solar system history. That changes the scene we reconstruct. Planet formation was dynamic. Growing worlds exchanged momentum, migrated through the surrounding disk, scattered smaller objects, and sometimes collided. Jupiter participated in that environment, while accumulating enough material to dominate the gravitational architecture around it. Saturn preserves a different record. Its atmospheric helium depletion reflects processes operating deep inside for billions of years. As Saturn cooled, helium became less soluble within hydrogen at certain pressures. Droplets separated and descended, releasing gravitational energy deeper inside the planet. Comparing Saturn with Jupiter lets scientists examine how planetary mass controls long-term cooling. Saturn is smaller and has followed a different thermal path. Together, the two giants provide separate experiments conducted by nature over roughly 4.5 billion years. Their influence also reaches worlds where liquid water survives far from sunlight. Europa circles Jupiter, while Enceladus belongs to Saturn. Both demonstrate that an ocean does not require warm sunlight at a planetary surface. Gravitational flexing can supply internal energy instead. That realization broadens habitability. The traditional habitable zone describes orbital distances where surface temperatures may permit liquid water, yet tidal heating can maintain buried oceans beyond that region. If similar moon systems form around giant planets elsewhere, subsurface ocean environments could be widespread. Jupiter's early history also shaped our own neighborhood. Its immense gravity influenced where material accumulated, how the asteroid belt evolved, and how small bodies moved through the inner solar system. Some models indicate that a solar system without Jupiter, in roughly its present role, could have developed a very different arrangement. The asteroid belt might have evolved differently, perhaps allowing more material to assemble into larger bodies. Earth's collision history would also change, including impacts involving water-rich objects during its youth. So when we examine Jupiter's diluted core or Saturn's evolving interior, we are reading more than planetary anatomy. We are reconstructing the forces that organized worlds, redistributed water and rock, and established the conditions from which our solar system emerged. The first planets found around other sun-like stars looked almost impossible. Several were enormous worlds, circling extremely close to their stars, completing entire years within days. Astronomers came to call these planets hot Jupiters, and their discovery forced planetary science to reconsider how gas giants move after formation. More than 5,600 exoplanets had been confirmed by 2024. Among the most influential discoveries were these close-orbiting giants. Conventional formation models place giant planet growth farther from a star, where colder material allows massive planetary cores to accumulate before capturing surrounding gas. Yet planets rarely remain exactly where they formed. Interactions with the surrounding disk can exchange angular momentum and gradually alter an orbit. A newborn giant may therefore migrate inward through its planetary system, sometimes traveling astonishingly close to its star. That possibility gives Jupiter's early movement a wider context. Models suggest our own giant migrated substantially before reversing direction. Saturn's growing gravitational influence may have helped alter that movement, preventing Jupiter from continuing toward the inner solar system. Elsewhere, migration sometimes appears to have gone much farther. A hot Jupiter can circle its star at distances smaller than Mercury's orbit around the Sun, some complete an orbit in only several Earth days. Their gravitational passage may scatter developing planets, rearrange smaller bodies, or prevent stable rocky worlds from surviving nearby. Other systems reveal equally unfamiliar arrangements. Astronomers have discovered multiple giant planets locked into orbital resonances where their periods maintain repeating mathematical relationships. Such configurations preserve evidence of migration while revealing how strongly neighboring planets can reshape one another. Atmospheric observations now let us compare their chemistry directly. The James Webb Space Telescope measures starlight filtered through distant planetary atmospheres, allowing specific molecules to leave recognizable spectral signatures. Water vapor, carbon dioxide, methane, and sulfur dioxide have all been identified in giant exoplanet atmospheres. In 2022, observations of WASP 39b produced the first detection of sulfur dioxide in an exoplanet atmosphere. Stellar radiation drives chemical reactions there, creating sulfur dioxide through photochemistry, meaning chemistry powered by incoming light. Similar principles help us understand reactions occurring within our own giant planets. These comparisons reveal something increasingly important. Our solar system represents one possible outcome among many. Some systems contain giants pressed close to their stars. Others pack several rocky planets into regions smaller than Mercury's orbit. Still others preserve distant giants whose arrangements resemble parts of our own system. When we place Jupiter and Saturn among those worlds, their familiar positions become scientifically revealing. Their migrations stopped. Their long-term gravitational relationship remained stable enough for smaller worlds to persist inside them. Earth eventually formed within that architecture. The planets around other stars, therefore, provide thousands of alternate histories. Each system shows what gravity, migration, chemistry, and timing can produce when the same basic ingredients follow different paths. For Juno, Jupiter is never a distant disk for long. Every close passage carries the spacecraft across a world whose gravity, radiation, and magnetism can reveal structures hidden thousands of miles below the clouds. That repeating encounter began with a launch on August 5th, 2011. After traveling roughly 1.74 billion miles, Juno reached Jupiter on July 4th, 2016. A precisely timed engine burn placed it into a highly elongated orbit. This path was chosen carefully. It lets Juno approach the planet closely, then retreat far beyond the most punishing radiation environment. At closest approach, called perigove, the spacecraft can pass only a few thousand miles above Jupiter's cloud tops. Its orbit is also tilted steeply, carrying Juno over regions previous orbiters could not examine with the same precision. From there, we can measure Jupiter almost pole to pole. Juno survives on sunlight. Three enormous solar arrays extend from its spinning body, spanning roughly 66 feet overall. At Jupiter, sunlight is about 28 times weaker than near Earth. Even there, the arrays originally supplied roughly 500 watts, enough to operate instruments, computers, heaters, and communications equipment. 9 scientific instruments turn each passage into a different kind of probe. The microwave radiometer measures radiation emerging from deep atmospheric layers, reaching hundreds of miles beneath visible clouds. A magnetometer maps Jupiter's complicated magnetic field. Gravity measurements track tiny changes in Juno's motion, revealing how mass is distributed inside the planet. Other instruments study charged particles, plasma, ultraviolet auroras, and infrared heat. JunoCam adds visible images. Although designed primarily for public engagement, its observations have become scientifically useful, while raw data allow citizen scientists around the world to create detailed, processed views. What makes Juno unusual is how directly these measurements connect spaceflight with planetary anatomy. The spacecraft cannot enter Jupiter and survive. Instead, Jupiter pulls on Juno differently depending on how material is arranged below. Radio tracking records those minute accelerations, allowing researchers to reconstruct features that no camera could photograph. The mission evolved as its orbit changed. A close encounter with Ganymede in June 2021 shortened Juno's orbital period. Europa followed in September 2022. Encounters with Io in December 2023 and February 2024 shortened it again, eventually bringing the period to roughly 33 days. Those moon encounters transformed an interior-focused mission into a broader exploration of the Jovian system. Juno examined volcanic activity, icy surfaces, rings, auroras, and magnetic connections while continuing its close surveys of Jupiter. The extended mission was scheduled through September 2025, or until spacecraft end of life. Its measurements have already altered models of Jupiter's atmosphere, magnetic field, gravity, and deep structure. From thousands of miles above the clouds, Juno has given us our closest, practical view inside a planet with no surface to land upon. Cassini's final transmission ended a conversation with Saturn that had lasted 13 years. By then, the spacecraft had transformed a distant, ringed planet into a complex system of weather, moons, oceans, chemistry, and moving ice. That achievement began decades earlier, with a machine built for endurance. Cassini-Huygens launched on October 15, 1997. Saturn was too distant for a direct journey using the available launch energy, so engineers designed a looping route through the inner solar system. Cassini passed Venus twice, returned past Earth, then received another gravitational assist from Jupiter. Those encounters changed its velocity without consuming enormous amounts of fuel. After traveling roughly 2.2 billion miles, Cassini reached Saturn on July 1, 2004. Its main engine fired for 96 minutes, slowing the spacecraft enough for Saturn's gravity to capture it. A 13-year orbital exploration followed. Cassini completed 293 orbits and conducted 127 targeted moon flybys. Its cameras returned more than 453,000 images, while instruments examined particles, magnetic fields, temperatures, atmospheric chemistry, rings, and moons. Titan became a world with rivers, clouds, dunes, and hydrocarbon seas. Enceladus revealed jets carrying material from beneath its icy surface. Saturn itself changed with the seasons. Cassini watched the North Polar hexagon shift in appearance as sunlight returned to the northern hemisphere. The rings became laboratories as well. Measurements revealed intricate waves, gaps, and propeller-shaped disturbances created by small embedded moonlets. Each structure responded to gravity differently, allowing researchers to investigate how countless particles interact within an enormous rotating disk. Eventually, fuel became the limiting resource. Engineers could no longer guarantee permanent control of Cassini's trajectory. Leaving an uncontrolled spacecraft near potentially habitable Enceladus or Titan carried a contamination risk from terrestrial microbes that might have survived aboard. So the mission adopted an extraordinary ending. Beginning in April 2017, Cassini performed 22 grand finale orbits. Each passage threaded the spacecraft through the unexplored gap between Saturn's atmosphere and innermost rings. Radio tracking refined measurements of Saturn's gravity, helping scientists separate the gravitational influence of the planet from that of the rings. The spacecraft also sampled particles falling from the rings and mapped Saturn's magnetic field at close range. Those measurements exposed unexpected complexity near the planet and helped constrain the ring's mass, composition, and evolution. On September 15, 2017, Cassini entered Saturn's atmosphere at roughly 70,000 miles per hour, instruments continued transmitting measurements during the descent. Atmospheric drag increased, thrusters fought to keep the antenna pointed toward Earth, and eventually control was lost. The signal disappeared. Cassini had become part of Saturn. Its mission cost approximately $3.9 billion across development and operations. Yet its lasting value lies in an archive, still supporting scientific research, preserving 13 years of observations from a planetary system that Cassini allowed us to examine as an evolving place rather than a distant point of light. The next generation of outer solar system exploration is already in motion. Some spacecraft are crossing interplanetary space today, while other missions exist only as engineering studies. Together, they are designed to answer questions that earlier probes could only approach indirectly. Europa Clipper left Earth in October 2024. The National Aeronautics and Space Administration spacecraft is scheduled to reach Jupiter in 2030, then repeatedly sweep past Europa. Rather than orbiting the Moon, it will use close flybys to examine the ice shell, buried ocean, surface chemistry, and surrounding environment. Instruments will search for places where ocean material may approach the surface. Another traveler follows a different path. The European Space Agency launched the Jupiter Icy Moons Explorer in April 2023. Its arrival at Jupiter is planned for 2031. The spacecraft will investigate Europa, Callisto, and especially Ganymede before entering orbit around Ganymede in 2034. That final maneuver will mark a remarkable first. No spacecraft has ever entered orbit around a moon beyond Earth's own. From there, scientists can examine Ganymede's magnetic field, icy crust, deep interior, and probable ocean with sustained measurements unavailable during brief flybys. Saturn presents a different challenge. No dedicated successor to Cassini is currently traveling there to investigate the planet's interior. One proposed approach is a Saturn atmospheric probe built to descend beneath the visible clouds and directly measure gases that remote instruments struggle to constrain. Jupiter could eventually receive an even deeper visitor. Scientists have studied concepts for atmospheric probes capable of reaching pressures near 100 bars, where 1 bar is approximately Earth's atmospheric pressure at sea level. Galileo's probe survived to roughly 22 bars in 1995. A deeper descent could greatly improve measurements of water and isotopes, atoms of the same element with different nuclear masses. Those measurements matter because atmospheric composition preserves evidence from planetary formation. Water abundance, noble gases, and isotope ratios can help distinguish where material originated within the young solar system and how giant planets accumulated it. Farther outward, Uranus has become a major scientific priority. The Planetary Science and Astrobiology Decadal Survey recommended a Uranus orbiter and probe as the leading new large planetary mission for the coming decade. Comparing an ice giant with Jupiter and Saturn would test whether our models truly describe giant planets as a family. New technology may extend that reach. More durable entry systems could survive deeper pressures. Low-frequency radio measurements may reveal interior structure remotely, while laser communications could return much larger volumes of data across immense distances. Titan also remains compelling. Concepts for later orbiters and lakelanders could eventually sample Kraken Mare itself, placing instruments directly within its hydrocarbon seas. With each mission, we gain another physical measurement of worlds whose interiors, oceans, and atmospheres still preserve material from the solar system's earliest construction. For most of astronomy's history, habitability followed the warmth of a star. Scientists imagined a band around each star where surface temperatures might permit liquid water. Jupiter and Saturn sit far beyond that traditional habitable zone, yet their moons have complicated the definition. Europa and Enceladus almost certainly contain global oceans beneath ice. Ganymede also appears to hide deep saltwater layers, while Titan likely contains liquid water beneath its frozen exterior. None depends primarily on sunlight to keep those buried reservoirs liquid. Their energy can come from gravity. As these moons travel around their planets, changing gravitational forces flex their interiors. That motion generates tidal heating, turning orbital energy into internal warmth. We therefore find environments where water remains liquid at distances once considered too cold for habitability. Life, as we understand it, requires more than water. It needs usable chemical energy and suitable building materials, including organic molecules. Enceladus provides evidence for all three. Material sampled from its plumes contains water, hydrogen, methane, carbon dioxide, salts, and complex organic compounds. The hydrogen is especially informative. Reactions between warm water and rock on the ocean floor could continuously produce chemical energy. Similar reactions support ecosystems around hydrothermal vents on Earth, where organisms survive without energy derived directly from sunlight. Enceladus gives us another advantage. Its ocean sends material through fractures and outward into space. A spacecraft can therefore analyze samples originating from below without drilling through miles of ice. In practical terms, the moon delivers portions of its hidden ocean to passing instruments. Europa may offer comparable opportunities if its suspected plumes are confirmed. Its rocky seafloor could also provide sustained water and rock chemistry. Any organisms there would inhabit conditions unlike Earth's surface. Darkness would be permanent beneath the ice. Pressures would increase with depth, and dissolved salts and gases could differ greatly from terrestrial oceans. Could life exist within Jupiter itself? In 1976, Carl Sagan and Edwin Salpeter explored that possibility scientifically. They imagined hypothetical organisms occupying atmospheric layers where temperatures and pressures become comparatively moderate. Their proposed ecosystem included sinkers, floaters, and hunters. Floaters were envisioned as enormous gas-filled organisms maintaining altitude through buoyancy. Sinkers would descend through the atmosphere unless they could reproduce or regain altitude. Hunters represented mobile organisms feeding upon floaters. These were theoretical possibilities, not detected creatures. The proposal remains highly speculative. Jupiter presents formidable obstacles, including powerful circulation, radiation, uncertain nutrient availability, and deeper regions where increasing temperature and pressure eventually destroy complex molecules. No evidence currently demonstrates atmospheric life there. Yet the thought experiment carries a useful lesson. Habitability cannot always be judged from sunlight and surface temperature alone. Around Jupiter and Saturn, gravity creates energy, ice conceals oceans, and chemistry continues far from the sunday. When we search these systems for life, some of the most promising environments may exist where sunlight never reaches at all. Scale becomes difficult when familiar objects stop being useful. Jupiter spans 88,846 miles from one side to the other. A car moving steadily at 65 miles per hour would need roughly 57 days to cross that distance. Crossing Earth's diameter at the same speed would take about 5 days. Even those travel times barely capture the difference. More than 1,300 Earths could fit inside Jupiter by volume. Every city we have raised, Every road we have paved, and every landscape recorded in human history belongs to that smaller world. Saturn challenges intuition differently. Its main rings stretch across roughly the distance separating Earth and the Moon, yet much of the ring system is only tens of feet thick. Imagine something extending across an enormous fraction of the space between two worlds, while remaining vertically comparable to an ordinary building. Planetary scale can be vast and delicate at once. Then there are places no human eye can ever visit. Deep inside Jupiter, hydrogen is squeezed under pressures millions of times greater than Earth's atmospheric pressure. Under those conditions, electrons move freely through the material, creating metallic hydrogen. We can briefly reproduce hints of such extreme states in laboratories. Jupiter maintains them across an interior region thousands of miles deep. Saturn may conceal another unfamiliar process. Models suggest that carbon can separate from atmospheric compounds at depth, eventually forming diamond crystals that fall toward hotter layers below. The idea follows high-pressure chemistry, although no spacecraft has directly watched such diamond rain occur. Some realities inside giant planets may remain accessible only through physics, gravity, and indirect measurements. The moons reshape our sense of scale again. Beneath Europa's fractured ice lies an ocean that may contain more liquid water than all Earth's oceans combined. That water may have remained there for billions of years, isolated beneath a surface that receives only a fraction of the sunlight reaching Earth. We still cannot say whether anything lives within it. That uncertainty belongs beside everything we have learned. Jupiter and Saturn once appeared through early telescopes as distant disks accompanied by points of light. Today, we understand them as layered planetary systems containing metallic fluids, immense magnetic environments, buried oceans, active geology, and chemistry unfolding under conditions unavailable on Earth's surface. Yet, knowledge has enlarged the unknown rather than erased it. Each measurement gives us sharper boundaries around questions that remain unresolved. We know enough to describe pressures no person could survive, oceans no camera has entered, and matter existing in forms we cannot naturally encounter here. Perhaps that is the scale worth keeping. The solar system is our immediate cosmic neighborhood, yet much of it remains physically unreachable. What we have discovered does not make these worlds smaller. It gives their distances, depths, and hidden processes meaning, while showing us how much of our own neighborhood still lies beyond direct experience. Earth's history cannot be separated cleanly from distant Jupiter and Saturn. Their gravity has influenced what entered the inner solar system, what remained outside it, and how planetary orbits evolved across billions of years. We live inside the architecture they helped create. Jupiter is often described as Earth's gravitational shield. Its enormous mass can capture, redirect, or eject comets approaching from distant regions. Some objects that might otherwise enter the inner solar system are scattered elsewhere, yet the shield analogy is incomplete. Computer simulations reveal a more complicated role. Jupiter can also disturb asteroids and place them onto paths crossing Earth's orbit. Depending on an object's original trajectory, the same gravitational power can protect Earth or increase its exposure. Jupiter acts less like a barrier and more like a powerful traffic controller whose influence reaches across planetary space. That influence was especially important during the solar system's youth. Around 3,900,000,000 years ago, the inner planets experienced an intense era of impacts, traditionally called the Late Heavy Bombardment. Evidence survives in ancient lunar terrain, where enormous impact basins preserve events that Earth's active geology has largely erased. One influential family of models connects this bombardment with orbital changes among the giant planets. As Jupiter and Saturn migrated, gravitational resonances shifted through populations of leftover asteroids and icy bodies. A resonance occurs when orbital periods interact in repeating gravitational patterns. Those changing patterns could destabilize countless objects and send some toward the inner planets. Earth received part of that material. Asteroids and comets may have contributed water and organic molecules during our planet's early development, although scientists continue debating how much arrived through each source. The same impacts capable of devastating a surface could therefore also transport ingredients relevant to later habitability. Jupiter still shapes the asteroid belt today. Its resonances create unstable regions where asteroids cannot remain indefinitely. Rather than forming a planet, the belt persists as a comparatively sparse population of rocky remnants influenced by Jupiter and neighboring worlds. Some fragments eventually reach Earth as meteorites. Among them are primitive materials dating back approximately 4,500,000,000 years. When scientists analyze these rocks, we are examining physical remnants formed near the beginning of planetary construction. Saturn gives this history another perspective. Its rings are temporary on astronomical timescales. If present estimates of their evolution are broadly correct, they may disappear within roughly 100 million years. Any observers living around the distant future sun could therefore encounter a Saturn unlike ours. Our particular solar system is a moment in an evolving arrangement. Planets migrated, small bodies collided, resonances shifted, oceans accumulated, and Earth developed within the consequences. When you look toward Jupiter or Saturn, you are seeing more than distant giant planets. Their gravity belongs to Earth's history too, woven into the circumstances under which our world became habitable and eventually came to contain us. For thousands of years, Jupiter was only a moving point of light. Babylonian astronomers recorded its path with remarkable care, building numerical methods that could predict where the planet would appear. They could follow its motion, yet the world itself remained unreachable. Then, in 1610, Galileo Galilei aimed his telescope toward Jupiter. Beside the planet, he saw small points changing position from night to night. Their motion revealed that they orbited Jupiter, providing direct evidence that Earth was not the center of every celestial motion. Saturn challenged that early telescope differently. Galileo saw strange extensions beside the planet and struggled to understand them. He described a form that seemed almost like three bodies joined together. The instrument could not resolve the true structure. Cassini-Huygens supplied the missing interpretation in 1655. Saturn, he concluded, was surrounded by a thin, flat ring that touched the planet nowhere. 4 centuries later, spacecraft would pass through the gap between those rings and Saturn itself, measuring gravity precisely enough to investigate structures buried thousands of miles below the clouds. That progression changes what discovery means. Better instruments rarely leave us with fewer questions. They replace broad mysteries with sharper ones. We once asked what Jupiter was made of. Now we ask how deeply its winds extend, how its dilute core formed, and why its magnetic field possesses such unusual asymmetry. Metallic hydrogen moved from theoretical physics into planetary models, then became part of a larger problem involving convection, rotation, heat, and magnetism. Saturn followed the same pattern. Its rings became understandable as countless orbiting particles, while its interior became less simple. Helium can separate from hydrogen and descend through deeper layers, releasing energy as it falls. Carbon may form diamonds under extreme conditions. Its core appears spread through a substantial fraction of the planet rather than ending at a neat boundary. Above it, the North Polar hexagon continues rotating. Beneath it, pressures transform familiar matter into states no person could directly experience. Across Jupiter, deep circulation and magnetic currents continue whether a spacecraft is measuring them or Earth is turned away. These processes began long before telescopes existed. They require no witness. That may be the most enduring invitation these planets offer. Science does not diminish the unknown by naming things. It gives uncertainty shape. Each measurement tells us where our understanding holds, where it breaks, and which parts of nature remain beyond direct reach. When you look toward Jupiter or Saturn, the light entering your eyes has crossed hundreds of millions of miles. Behind that light are interiors no camera can photograph, histories no observer watched unfold, and physical processes reconstructed from gravity, magnetism, chemistry, and mathematics. The worlds were there before we understood them. They remain larger than our explanations. For this brief moment, we have instruments capable of reaching them, minds capable of asking what lies beneath, and the remarkable privilege of looking.